So, anybody get an answer?
Would it be 3b1, 3b2?
No. So here, I'm glad one of you said that, because now let's just, the magnitude is 3. Okay, so the total magnitude would be 3. So if, let's say, here's b1 and here's b2, then we have the vector b. And like, if that's like 10 and that's 5, if you multiply that by 3, it's going to get even longer, right? So that's not what you want to do. Right. So like, for instance, and let me just be explicit here, right? So if this is say 4 and this is say 3, then the magnitude is what?
Root 5. Just 5.
Root 25, so it's just 5. That's why I picked that one. And if you then multiplied that each by 3, you'd have 4 times 3 is 12. 3 times that is
9.
Thank you, 9. And now you've made it even longer, right?
Yeah.
It would be, your total length would be 15. So you can't just multiply it by 3. Though you'll want to multiply something by 3.
What I did is
What did you do?
I just said b1 squared plus b2 squared equals 3 squared, and I just solved for them. Like because if the magnitude is 3, then b1 squared plus b2 squared.
But then you have 2. But okay, so you're saying b1 squared plus b2 squared equals 3. Then, but now here's the thing: you have 2 variables here.
Well, just
in other words, you have an x squared plus y squared equals 9. Anything on any vector on this circle would work. And so it couldn't be in the same direction as the original. Because now you have 2 degrees of freedom. You see what I'm saying?
Yeah.
And so here's the thing. What if this length happened to be 1? Then you would just multiply it by 3. Then you just take it and multiply it by 3. Can we make this thing? Can we find a vector that's, and this is the thing, is in the same direction? So in other words, what we're trying to do is just scale this vector by some amount, but we need to figure out what that amount is. If this thing happens to have length 1, then all we have to do is take whatever that vector is and multiply it by 3.
So if we
divide by the magnitude.
There you go. That's the trick here, right? Is that if what we want to do is start with the unit vector in the direction of of b, sorry. So we take our original b, and what did you say we divide it by?
The magnitude.
The magnitude right there. So this would be, now, if I didn't say explicitly find a vector, in other words, I'm looking for the actual components, this would be that. And then we'd take this and multiply it by 3. And that would be, in fact, and we could stop there. I could just put a 3 right there and that would be done. But I want it explicit. So let's be explicit here. 1 over, what is the magnitude?
The square root of b1 squared plus b2 squared.
There we go. And so when I put that in there, then the unit vector in the direction of b. So if this is b, and I didn't say, it might be really small. This might be 1/10. And that might be 1/20th, in which case the unit vector would actually be longer, right? But we'll just pretend here that this is b hat. And what I'm going to do is I'm just going to distribute that into there, right? And I have b1 over root b1 squared, b2 squared, comma b2 over root b1 squared, b2 squared. Now that we know that this has length 1, what do we need to do to find it?
3.
Multiply this guy by 3. So then the vector I'm looking for would be what happens when I take this guy and multiply him by 3. So I'm going to stretch out a unit vector by 3. And that should give me 3b1 over root b1 squared, b2 squared, comma 3b2 over root b1 squared, b2 squared. That's the c that I'm looking for. So now we filled in those blanks right there. Now, if I didn't say explicitly, what you could have done is just said, well, I need to shrink this guy down or stretch, right? Because, like I said before, if it turned out that we had something like, I don't know, let's make this 1/10 and we'll make this 1/20. Okay? Well, now it's pretty clear that that thing is shorter than 1. And I could say, okay, the magnitude of b is then the square root of 1/10 squared, so that's 100, plus 1, 2, what's that, 400?
Yeah.
Something like that. And so then 1 and 4, I guess I could do a 4 and a 4, so that would be 5 over 400, root 5 over 400.
So root.
And so that's root 5 over, that's 4 times 100, so 2 times 10, so 20, yeah, thank you. Okay, and so that would be the magnitude of it, clearly shorter than 1. But then when I divide by that magnitude, right, I would take my original b, which is 1/10 over 1/20, and I divide by that. 1 over that's the same as the reciprocal, right? If I go 1 divide by that number, right, that's what I'm doing there.
Yeah.
1 divide by that number is the same thing as multiply by the reciprocal, so that would be 20 over root 5, and so now we have 20, 10 root 5, 20, 20 root 5. I guess that cancels, that's 2 over root 5, 1 over root 5. And so now I would have to stretch this guy out by however much by doing that, right? But at any rate, either way you want to do it, if you divide by the magnitude, you end up either stretching or shrinking the thing so that it becomes a unit length. So in general, we have B1, B2, right? And then that's what we do. So something very similar to this, maybe even exactly this, will be on the quiz. I'll tell you explicitly. And I'm looking for the components here. I want a vector either in the same direction or opposite direction, maybe, that has a given magnitude. And like we talked about in class, right? Like, there's another way they said this, that like you did one's problems at home that said, find something in the direction of B that has 3 times the magnitude of B. Right? And then in that case, yeah. That's 3 times the original magnitude. You would just multiply that thing by 3 to stretch it out by 3. But that's not what this says. We want the magnitude of exactly 3. And real quick, we could check this just to make sure that it does have magnitude 3. In fact, I'm going to do that. I'm going to get rid of all this stuff that we have except for the actual answer we got. And then I'm just going to check that indeed its length is 3, because that was magnitude is 3. That's what we wanted. So, okay. Magnitude of C is equal to the square root of some stuff squared plus some stuff squared. This stuff is that, so we have 3b1 over the root b1 squared, b2 squared. 3b2 over root b1 squared, b2 squared. This is the same as 3 squared is 9. b1 squared is b1 squared. This is just now b1 squared plus b2 squared. This same thing, 9 b2 squared over b1 squared plus b2 squared. We have a common denominator. Easy. b1 squared, b2 squared. Common denominator. So when I add those together, it looks like I can pull out a 9. So I'm going to go ahead and do that. I'm going to pull out my 9.
And then those cancel.
b1 squared, b2 squared. And I'm going to make sure, does that really cancel? Yeah, it really does, because I have multiplication on top, right? It's not like I have b1 squared plus b2 squared plus 9 over b1 squared plus b2 squared. That would not cancel, right? Because you can't factor out a 9. This does cancel. We get root 9. Understanding that this is always positive, you're taking the positive square root by definition, you get positive 3, which is what we want. right there. Okay? So one thing I just want to say, because if we have time, we might come back to this, and this is something that you won't be quizzed on, and if we have time, we'll come back to it just so you can see it again. The takeaway here is given some vector, you have the direction of some vector, right? If you want to stretch that or shrink it to a vector with a new magnitude in the same direction, right? What you do is you first, you find the unit vector, right? That's like step one. Step one is find unit vector. And then two is you multiply that unit vector by whatever that new magnitude you want, right? Whatever the final magnitude you want, that's what you do. You multiply it by that. So in other words, you take your new magnitude, multiply that by this guy right here, right? So in other words, M that B. I'm just reducing it. It doesn't need to be written this way. I'm just saying that's what you would do. Find a unit vector and then multiply by whatever that final magnitude that you want. And that gives you a vector that's in the direction of the thing you care about, for whatever reason you want to do that, and it has the magnitude that you want. Everybody got that? Yeah. Okay. We may or may not come back to that. It won't matter if we don't. So, okay, here we go. Let A equal 1, 2. And let's let B equal 3, 1. Now we're going to do a bunch of things with these two vectors. First thing, what's A dot B?
3 plus
5.
2. Yeah.
So you take that one times that 1 times 3
Plus.
plus
2 times 1.
1 times that 2 times 1. And you said that that gives me 5. So in other words, A dot B is a scalar, right?
Yeah.
A dot B is not a vector, right?
Yes.
Right.
Okay, so it's not, you're telling me that this is not equal to the vector 3, comma 2, right? That's what you're telling me?
Yeah.
That the dot product is not equal to a vector?
Yes.
Right.
The output's a scalar.
Right.
I feel like that's
Right,
important.
right. So, in other words, like if you had, say, something like this. And I told you to find the dot product.
Do you want to just do this?
It would not, you're telling me it would not be equal to A1, B1, comma, A2, B2, right?
Yeah.
Yeah, because it's not a vector. It's not this is never equal to a vector. It's always equal to a scalar. And just because you don't have the actual numbers here, doesn't mean that you could put them into a vector. Like what it actually is, what it is indeed equal to, and like you told me to begin with, is it's what you'd get if you did that. If you added them together and it gave you a scalar, right? It's not a vector. Okay, just want to make sure we're all on the same page here.
Did we mess that up?
Somebody messed it up. And then that somebody didn't mess that up when you got actual numbers to put in there, but when it was symbols like A1 and B1 and such, it was like, oh, this is a scale, this is a vector. No, it ain't. Okay, so it's not ever the case that you dot two vectors and get a vector. It's always, always, always a scalar. Okay, now, to address another problem we had. Find the angle between A and B.
So,
Okay.
graphic, that's what I...
Ooh, you want to graph it? Okay, so that's one way. That's one way we could do it. Let's do it. Now, let me show. So first off, here's. Let's do the easy way first. The easy way is to use this fact that, and I'm not. I don't need to write. In fact, I'm going to write it down here so that, just to show, like we're not. There's a fact that A dot B is equal to the magnitude of A times the magnitude of B times cosine theta. Therefore, cosine theta is equal to A dot B over the magnitude of A. B. Understanding that theta is the angle between them. We're gonna say, in other words, theta, find that angle. And so it's the case that you could just do this. You could say, well, then A dot B we already found was 5, right?
Yeah.
What's the magnitude of A?
5.
Root 5. What's the magnitude of B?
Root 10.
Root 10. If that's equal to cosine theta, then theta is equal to arc cos of this. And on the quiz, I just want to say this. On the quiz, you will not use calculators. This will be what I'm looking for.
Exactly.
Okay? So boom, that's it. We are done.
But there's another one.
We are so done. Now watch this. Now this is the thing. This is the thing. So that's the easy way. Did you see how quickly I did that? Now watch this.
Oh.
Here's the hard way. Here's the hard way. Now, and I'll show you why. At first, it's not going to seem too hard. It's not going to seem too hard. And it's not that it's wrong. What I'm about to write is correct. But I want to talk about this. And I want to bring this up. And don't think I'm picking on you guys. Because it's actually good that this has happened. Because it's going to give me a great way of illustrating something cool. So this is cool. So another way of doing this is, okay, we're looking for this angle theta. Obviously this is A and this is B. Okay. Now what we could do is say, well, here's this angle alpha. From here to here is this angle beta. And therefore theta is equal to what? In terms of these two.
Oh, beta plus theta. I mean beta plus alpha.
Plus?
Or wait. Beta minus alpha.
Beta minus alpha. And you see already it's like, ooh, that could have been a mistake that that you could make just by looking at this thing the wrong way. But it's true. There's beta and there's alpha. Now beta would be arctan of, let's see. So this one's beta, so how about 2 over 1? 2 over 1. Alpha would be arctan of what?
1 over 3.
1 over 3. And so you could answer that theta is equal to arctan. Instead of 2 over 1, I'll just call it 2 minus arctan 1/3. And you would be absolutely 100% correct. But watch what happens. Let's say instead of A and B being that, what if B were the same, but in this case, A is -1, 2.
Then it gets weird.
Well, watch what happens. So we go -1, 2, here's A. And here's B. B is still the same, it's 3, 1, here's B. Now we have theta. Oops. Now we have theta. Now we have some choices, and I could say, just by looking at this, I could see this one's going to be easier. It's the height of 2. I could say, okay, we'll make this alpha.
Oh, and then
We'll make this beta.
and theta's
Theta's what?
180 minus
Uh-huh.
alpha minus beta.
Minus alpha minus beta. Yeah, because in this case, you have 180 degrees this way. If you minus off alpha, minus off beta, what's left is theta. And so now we have alpha is equal to arctan of what?
2 over 1.
2 over 1. And beta is equal to arctan of what?
Negative. Wait, no.
There's no negatives when we're doing it like this.
Just 1/3, yeah.
1/3. Because that's the idea. We're trying to measure this angle. That is like separate from the whole idea. It's just that's a triangle, right? And so we're abstracting here and saying, well, if you had a triangle with that, you would find it by saying positive that over positive that.
Yeah.
And that's what we did. And so you'd say, okay, then theta is equal to 180 minus arctan. I'm just going to do atan. It doesn't matter either of them. 2 minus arctan 1/3. And you'd be right. You'd be 100% right. Now, what if B's the same, but now A is equal to -1, -2? And so, let's see what that would look like. B is 3, 1, and you have B. Now you have -1, -2. Now check this out. Here's theta. Huh.
Oh.
It's hard.
It's
Right.
very hard. Because watch. Let's just start here and say, okay, here's beta.
B.
If I could maybe make this one alpha. In which case,
9. Wait,
theta
could make the
is
other one alpha.
equal to, or I can make this one alpha.
And then it would be 90 plus both of them, right?
Alpha, and so then,
Yeah.
okay, so let's see.
Yeah.
So then 90 plus beta plus alpha. So 90 plus beta plus alpha is equal to theta?
Wait,
Yeah.
what?
Yeah, so look, check it out. Theta is from here to here. From there to there is 90. If you take 90 and add on alpha, you get to there.
Oh. Yeah.
And then you take that, add on beta, you get to there, right? The thing is, though, look at how different each one of these are. And we even messed up this beginning one, right? It was like, oh, alpha plus beta equals that. Oh, wait, no, it was which one minus which one? This one minus, and this one's that. So it's not that you can't do it, and it's not that you won't get to an answer that's correct. These are all correct. Every one of these is correct. It's just, there's not a good way to generalize this. But watch out. So now remember how easy it was to use cosine? Right? It turned out that theta was equal to arc cos of whatever a dot b over
The
magnitude
reason I
a
used
magnitude b.
arctangent is because I just didn't want.
We're gonna talk about that because something so cool, and maybe if you guys are really good, at the end of the year we'll be able to prove this thing that I'm gonna talk about. But so yes, and I'm gonna address that in just a second. But watch this, because here comes the nail in the coffin. This is. So let's say that you're willing to say, you know what, it may get me a little mixed up in the head, but at least I feel good about it, and I could use this method where I draw it out, and then I find, do whatever I have to do to find alpha, find beta, and then figure out what theta would have to be. What happens when A is equal to 1, negative 1, 2, and B is equal to negative 2, 2, 3. Let's take a look at what that would be. We have two vectors. Now we're in three-dimensional space, and we want to find the angle between them. So you say, well, I know my method. This is the method I like to use. And so you do this, and you say, okay, here's my x, here's my positive y, and here is, actually, let me make it a little bit longer. Make it a z right there. And so A is going to be, I go 1 in this direction. I go negative 1 in this direction. Oops, that looks terrible. Negative 1 in that direction. And then I go up to here. And so there's A. Now I go negative 2 in this direction, 2 in this direction, it's over here and here, and then I go up 3 in this direction, and so I have a B. There's theta. Good luck. Good luck! Because this thing is like, one of them's kind of out this way, the other one's back this way. You might be able to find a plane that goes through, but then even then, if you did find a plane, and I think it does work out that there is a line that goes right through there. Even then, now you'd have to find, okay, here's this thing. It's not always going to work that way either, but here's the idea: is like if it weren't on a line, you're completely screwed. If it happened to be on a line, now you have to find that angle and find that angle, but that's different. So you'd have to find that length and that length, or you could say theta is equal to arc cos A dot B over magnitude A, magnitude B. And in this case, A dot B is negative 2, so negative 4 plus 6 is 2. That's a 4 plus a 1 plus a 1, so 4, 5, 6, root 6. This is a 9, 10, 11, 12, 13, 14, 15, 16, 17, and you're done. And it works in every dimension. So, I'm going to suggest that you guys get good at this one right here. Now, like I said, I want to, so I know that I have said anytime you can, and I really drilled this into your head. I said, anytime you can use arctan, you should use arctan. I guess in one sense, what I meant by that is you have some kind of setup of a triangle, and you're trying to find theta. And if you know that you have, say, let's say we have all of them. Let's say we have this is a 3, this is a 1, making this a root 10. And you want to find that right there. You could use arc cos, which would be that, right? You'd say theta is arc cos, that over that, 1 root 10, or any of them. But you have the choice. And so I would suggest always use this one. Always say, that one is pointing at the thing. Yeah, I would say then theta is arctan. 3 over 1 is 3, right? So, but even in other scenarios where you might have to do a bit more work to get arctan, I would say use arctan whenever you can. And why did I say that? Why?
Because there's no limits on the input.
Exactly, thank you. So arctan, in other words, the domain of arctan. In other words, the allowable inputs to arctan are all real numbers. You can take any real number, throw it into arctan, and you don't have to worry about it. Whereas maybe you set something up a weird way and you go to plug something into arccos and it's bigger than 1.
And you have to do all
Bad
the
news. This is one of the only times I'm going to say it's better to use arccos. But you might say, well, yeah, but what are you're saying, so you're telling me, Justin, that you should always use this, A, B, but what if what's in here turns out to be bigger than 1, or less than -1? Turns out, there is a very famous inequality called the Cauchy-Schwarz inequality. Yep, Cauchy, these are names. Cauchy is a very prominent dude in analysis. Schwarz was also Cauchy-Schwarz, and I'm going to have to Cauchy, the Cauchy-Schwarz inequality. And if you ever take a class in analysis, you'll prove that this thing is true, and then you're going to use it in every other thing that you do. It turns out that this is true for every vector in every space. Doesn't matter if it's a 3 vector, if it's a whatever vector. You take the absolute value of the dot product, which is a real number, right? You take a real number, and it is, the absolute value of it is less than or equal to the magnitude, the product of the magnitudes of the vectors. But now, what does this mean? If you have absolute value of x is, say, less than or equal to 5,
That means it's like
x is what?
in between.
It's
5,
in between what?
5 and -5.
There you go, right, 5 and -5. So, this means that this thing, A dot B, is between that product, whatever it is. It's just 2 real numbers, it's just some number times another number, or the negative of it. Negative A, B, like that. Dividing both sides by this number. By the way, without that negative there, that's a positive number, right? Because the magnitude's always a positive number. So you divide both sides by it, and you get that's always true. And therefore, no matter what this is, no matter what 2 vectors you took, you do that, plug it into there, you will always have a number between 0 and 1. I mean, sorry, between -1 and 1. And you could plug it in, and it's always defined. And since this is so simple to use, I'm going to suggest that anytime you're trying to find an angle between 2 vectors, always use this guy. Thanks to the Cauchy-Schwarz inequality. And if we have time this year, I would like to prove this. It is a doozy. It is so hard. It is one of the hardest things I had to prove in analysis. And then like after you do it, you're like, oh, Yeah, okay, yeah, okay. I don't know, maybe it's just my brain just wasn't working with it, but you could prove that this is true. And you could do it in general, not just for like two vectors, you know, like where your vector A is A2. What we'd be proving is that it's true for when your vector looks like this.
Yeah.
When you have an arbitrary number of entries in your vector. So, that's cool. Okay, so I wanted to talk about that. I'm glad we talked about that. And if you happen to use tangents and stuff like that, I commended you. I wrote it on your homework. I was like, that's good. You did a very good job. You listened, and you listened to me. Thank you. Like, yes, like it's like arctan's always good to use. It's really good to use. But there's one case, like this is the only case I could think of where you don't want to use arctan. And I wanted to show you why. Like, 'cause when you get some higher dimensions, good luck. And you can imagine you did 4. If you have a 4, you know, 2 vectors in 4 space, you can't draw it. You know, what are you going to do, right? And so it turns out that that nifty little formula works for all. Yeah. Okay. So for the quiz. Be able to prove the statements in the boxes. And these were on page 595 and page 606. You had better be able to prove every single one of those to my satisfaction, right? Like, if you got a comment on one of yours that you've done, and then you will either receive now or have received back from your homework, you'd better iron that out. And if you have any questions about that, you had better get to me. It would be good if you got to me sooner rather than later. Like, Monday nights are crazy for me. So, it's going to be super crazy because we're changing Pete's schedule. So yeah, it's good. Monday nights are going to be terrible. It'd be great if you get to me before that with any questions that you have about that. Okay? All the homework problems, all the homework in 8.3 and 8.4 is fair game. It's fair game, okay? No calculators, so don't worry about that. I'm not looking for any kind of crazy stuff. I just want to know that, like, if you show me, like we did earlier, right? Arc, cos, you told me that the answer is 5 root 6 root 17. I believe that you could plug that into a calculator. And so if you just write that, we're done. Okay, that's good. Something like that is what I'm looking for. Exact answers only. Now, since that's the case, let's do number 59 from, I didn't write what this was from. It was from, I'm not sure which set, but when I write it, you'll see. I think it might have been the first, this might have been from 8.3. But the setup was this. Force 1 is given at 130 degrees right there.
Oh, right.
Yeah. And it said it was 6 units long. Force 2 was 4 units long. We're going to call it F2. And it gave you this right here and said it was 120. Now, we're trying to find the net force. What is a net force?
F1 plus F2.
Yeah, just those two vectors. So we're trying to find F1 plus F2. If I give you something like this, I'm just going to say find the net force. I'm not going to tell you do this. Like, you should know when I say find net force, you're just adding together all the forces, okay? And then the homework said find a G, which is equilibrium. So in other words, you just make the vector negative. Whatever, we're not going to do that right now. Now here's the thing. I have this nifty. So, no matter where your vector is in the plane, right? Let's think about this. Let's say we have a unit circle right here. 1, 1, negative 1, 1. And it doesn't matter where it is. In fact, let's just make it right here. And let's call this angle right there theta. Then this point is where? It's what comma what?
sine theta, cosine theta.
Which
Or-
one's first?
Oh, sine, right? Cosine's first.
Cosine's first. Cosine's the x.
Oh yeah. Cosine.
Remember cosine, because if you think about theta being 0 and you're just watching the x values, it starts at 1, shrinks down to 0, and then goes down to -1, right? Whereas sine was the one that we projected this way, right? If you watch this dot and you're shining a light, it starts at 0, and as it moves up and then comes down. You guys remember that little animation thing I did on Desmos, right? That's where all this comes from, right? So then cosine theta is the x component of that. If you're imagining a vector now, right, it's the same thing. Then this vector would have the coordinates cosine theta, and by definition, and this is how we ended up defining them in general, remember? Because I said, we'll start off by defining sine and cosine in terms of triangles, but then we're going to open up that definition so that we can put in any real number value into it. And when we did that, then we said, forget all about the triangles. From now on, our definition is going to be its point right there. Okay? Now this is if the radius is what? Is if it's 1, right? So now let's take that, because now we're just talking about a triangle. It has hypotenuse 1, and it has an y value and x value. And now let's just stretch it by a factor of 6, let's say. Okay? So now I stretch this thing by a factor of 6. I multiply it by a factor of 6.
And then you.
So if I take this triangle and I multiply this number by 6, what do I have to do to this one?
Multiply by 6.
That was the first thing we did, right? That was the day one. That's what we did. We said anytime you stretch a triangle, you can keep that angle the same, and if that angle's the same, then this is going along like that. And so, really, instead of it being cosine and sine, now what are the coordinates out here? Because I multiplied it by 6, so
6 cosine.
6 cosine theta, 6 sine theta. Doesn't matter where we are on the unit circle. All that matters is that you are measuring it from here. And so this one's nice because it's measured from there. That one's not, because it's not measured that way.
You could
So,
be 360 minus.
yeah, there you go. And so as long as you're doing it that way, right, because it'll work if your phi, we'll call this angle here phi. As long as phi is measured from the positive x-axis all the way around to here, then you're good to go. You just plug it in and you're good, because that was the very definition of sine and cosine. So this guy came out to be, it would be phi instead. So that's cosine phi, sine phi right there, as long as you're measuring it from there to there. So really this becomes very simple. So you guys tell me, what's F1 as a vector?
Wait. 6 times cosine of 130.
6 cosine 130.
6 cosine of.
6 what?
Sine of 130. Yeah.
Sine of 130. That's it. That's what I'm looking for. That is all, because we don't have calculators. I don't care what those evaluate to be. That's the answer. So if we could get the other one in this form, measure that guy around that way, then F2 is going to be just as simple as that. And so, what would it be?
360 minus 100 is 240.
I think 240. I think that's what I got. Is that what I got? Yep, 240. So make sure you do that right. I'll be forgiving because it's a quiz, right? This is 240 now. If we go around 240, then what do I put here? What's the first component?
4 times
4 cos
2 cosine 240. 4 times sine 240.
4 sine.
Then we add 4.
There we go. And now what do we get when we add them?
Just then plus
We
each
get
other.
10. Yeah, we just
6
You
cosine 130 plus 4 cosine of
There we
240.
go. 6 cosine 130 plus 4 cosine 240. Notice it's not 10 cosine something, because those aren't the same, right? Like, if they happen to be, like, in the same place, then yeah, like, but it's not, right? it's not the same. So in general, you can't say that that's going to work. There is a place where that, because the cosine's the x value, there would be a place where they would be the same if it's just right. You can't, but I don't care. Like this is that. I believe you could plug that into a calculator. And so then what's the other one?
6 sine 130 plus 4 sine 240.
And that's what I'm looking for. Okay, that'll be a perfectly good answer. If you want absolutely 100%, you should.
It's not 240 radians.
It's not 240 radians. There's a difference. Okay, so I think that was about it. Like okay. Now here's the thing. Like I mean, since we do have 120, we could, if we were so inclined, we could find an exact value for this guy.
Oh, right.
Because this would be 30 degrees. This would be 60 degrees. So if you were so inclined, you could set up either of those triangles and say, well, if this is 60 and this is 4, then this would be, I guess, 2, and this would be 2 root 3. And so you could answer it that way. I don't care. Like, this is not the point of that, right? Not for this one. Like, trust me, soon enough, we'll be dealing with this, and you'll be sick of it, and you get so much practice with it, it'll be fine. For right now, just do this. You tell me how you would find it in a calculator, and we're good to go. Okay, questions on this before I get rid of it? It's gone. Okay. We actually have time to talk about the thing I wanted to talk about. So earlier, I said, actually, let's get back up to what I had on the board to begin with. So I said, we're going to let B be some vector, and what we're looking for, and so we're imagining, okay, here's a B. There's your vector B. And what we're imagining is, okay, we either need to shrink, we want a vector C that's in the same direction as B, but it has magnitude, but with magnitude, some given number, let's just say M. And what was the first thing we needed to do to figure this out?
Make it a unit vector.
Right, we want a unit vector. And so we did what?
Divide by the magnitude.
We divided it by the magnitude. Okay, so that was step one. We divided B by its magnitude. And then what did we do to get the final C that we wanted?
Multiply it by M.
We multiplied it by whatever that magnitude was that we wanted. So we just said M times B hat right there. Okay? Okay, so that's where we were. Now, let's do this. Here's A. Now you remember, if I said that if I took a light and shined it so that this came down at like a right angle right there, in other words, and I tried not to say this too much, if I projected this guy down onto here, then that length right there, we had a special name for it. What was that? What was the length called? The component of A along B. Now, let's say I want a vector C that's in the same direction as B, but... Alright, so that means we have 9 minutes. So I want a vector C that's in the same direction as B, but it has now that length. So let's just see what we have to do. We'd have to say, well, then the vector that I'm looking for, C, like you said, it has the magnitude that you want, and then we multiply by B hat, which happens to be 1 over B, right? The normal. We normalize this vector. Yeah? But now that M that we want is actually the component of A along B. And we had a nifty formula for this. What was that formula?
It was
Magnitude, well, it could be A dot B over
There we go.
magnitude B.
A dot B over what?
Magnitude.
Over the magnitude of B. Okay. So now, wait just a second. Is that a vector?
No.
Is that a vector?
No.
nothing.
Is that a vector?
No.
So those are all just real numbers. I could just multiply them all together.
Yeah.
But that's a vector. So really, we have some magnitude out in front of a
So
vector,
it's all
right?
scale.
So those are all just scalars. So let's just multiply them together. I get A dot B over, what's something times itself? We have a special symbol.
Squared.
It's whatever that something is and we square it, right? Okay. And then we take that, that's the new magnitude. And here's B. So that's your M. That was the, well, I guess not. That was, anyway, that's the magnitude of the thing that you wanted. B squared. How do we write some vector magnitude squared in terms of a dot product? It's what dot what?
B dot B.
B dot B. Yeah, it's B dot itself, right? Everybody with me on that?
Yeah.
Right? Because if I said B was B1, B2, and we dotted B with itself, we would get B1 times B1, or B1 squared, B2 times B2, or B2 squared. And that's exactly what the magnitude of B squared is, right? So we've seen that before. So I could rewrite this again and call this A dot B over B dot B.
Cancel.
No, it does not work like that. It absolutely, that's another thing, right? You say, oh, do those cancel? No, they do not. Because this is not, well, first off, we don't,
They're not.
like, you would have to try and prove that. But this is one of those, this is a really good thing. This is where vector multiplication, you're not really multiplying vectors, but this is where that breaks down. Like up until this point, we had like A dot B plus C, and your intuition tells you, well, it should be A dot B plus A dot C. And it turns out to be true. If you then said, well, this should be, those should cancel, and you just have A over B, you have a vector divided by a vector. Did we ever define what that meant? No. So this is where that kind of stuff breaks down. And now this is some scalar divided by some scalar. And you can't reduce that anymore. It's just the way it is. But the cool thing is, look at that. Now, this vector C has a special name the same way. Notice that this is a vector. This is not a length. This is not a scalar. Because you're taking a scalar, whatever it happens to be, multiplying it by a vector. This was a scalar. Yeah? But this is not, and it has a special name. It's called the projection of A onto B. Yeah, your book doesn't go into it, but you'll see it eventually. The projection of A onto B. And you'll notice that it's very, very similar. And look at this guy right here. It's very similar to the component of A onto B. I mean, obviously, if you went and found the length of this guy, you would find that it is the length of this right here, which is A dot B over the magnitude of B, right there. Right, so we have these two nifty little formulas. You will see this one eventually, but we're not going to do it in this class. And I was going to start off with this because it would go right after what we did first, but since it's not necessary, I'm not going to quiz you on this. I just want you to see it. Yeah. So that's projection of A onto B. And I kept saying, so if you projected this vector onto here, and I was like, ugh, if you shine a light, because I didn't want to like confuse the two, right? Because this is what happens when you actually project a vector, you get a vector. The length happens to be what we call the component, but that itself, this vector is called the projection of A onto B. And its length is component of A along B.
Will the component stuff be on the quiz?
You better believe it. What did I say? Everything in the homework is fair game. So, you better know how to prove that stuff. Now, since we have a little bit of time, I'm glad we have a little bit of time because this is something I wanted to talk about. We've been talking about vectors in terms of force and points and stuff like that. They really, anything could be a vector. If you recorded Beethoven's Ninth Symphony, well, that's the fourth movement. The fourth movement is Ode to Joy. But what happens is like there's sound waves, right? But what you do is usually most music is sampled at 44,000 hertz. So that means 44,000 times a second you're taking a sample of what you're hearing. You understand that this is supposed to be a sound wave?
Yeah.
Right? Okay. And like
like
what you
mountains.
have, and it's usually normalized so that the biggest amount you have is 1, the smallest amount you have is -1. Like, and we're talking about the loudness here. This is the loudness that you're hearing. But if like you were to look on your hard drive, if you have Beethoven's Ninth, or any piece by Beethoven, or any of them, it could be Bach. No, but you have any music. What your computer does is or what digital media does is it samples, right? It takes samples and it collects each of those samples in a vector. And like what this is, like a track of Beethoven's Ninth Symphony will just be a series of entries. And so let's say this is like 0.1, this is like 0.207. What you'd have is just this 0.207, 0.83, 0.99, and so on and so forth, all the way until the final dun dun. I think that's how it ends. No, there's something else.
I think
after
they all
Ode to
kind
Joy.
of.
Yeah, right? Until the final bit, right, which this says is 0. And so that vector, it's a string of values, but it codes for sound. And you could think about like this vector is just a collection of sounds. I mean, it's a collection of sampled points along this waveform. Ditto with seismograms. This is what my wife does for a living. Is like she looks at stuff like this. And they take like raw data because they have these stations that are out in Washington or wherever, and when they move around, it collects data like this, and it samples at some certain frequency, and then this is the vector that she has and she works with. Like it's not so much. So sometimes you could think of a vector as like this thing that's pointing in a certain direction and it has components, but not like that's not the only way we could think about vectors. It could be just a string of values that you have from, say, sampled a seismogram, or Beethoven's Ninth Symphony, or his Fifth Symphony, not as good as his Ninth, but, you know, that's debatable. That's debatable. We'll get into that. We'll get into that another time. Okay, so now, here's one, so it's time to go, but there's one more thing I want to say. This is what I did after my undergrad. This is the kind of stuff I started doing. Let's say we have a picture. A digital picture. And to make things simple, let's just say that this picture has 4 pixels. Very small picture. But and let's say it's a grayscale picture. It's just gray. So the way most computers work is that, and yes, you usually have red, green, and blue, but we can generalize that in a minute, but right now, let's just say we have a gray picture. So then each one of these pixels is depending on its brightness. If it's not bright at all and it's completely black, then we give that a 0. We would say, so if this pixel were completely black, we'd give it a 0. And if, let's say, this pixel were completely white, we'd give it a 255. So there are between 0 and 255, so there's 256 shades of gray that you could have, where 0 is completely black, no light is being on. 255, the light is all the way on. And then you have something in between. So like you have like maybe 128, which is kind of a gray. And maybe you have like a 150, which is also kind of a gray, whatever. But what you could do is say, given any size of picture that you have, this one happens to be 4x4, 2x2, whatever, you could just say, you know what, start with the top left one, and move across the first row, then move down a row, and move across there. And from there, you could record what this thing is. And so you go, okay, then this would be the vector 0, 128, 150, 255. And there's a one-to-one correspondence here, because once you have your scheme, I could give you any one of these. I could say 10, 13, 201, 250. And you could say, okay, given that, I could reconstruct a picture. And I could just tell the computer, okay, take this first pixel here, understanding that we're talking about a 4x4 picture. It would be different if we were doing a 9x9 or a 900 by 1600, but we would say, well, you just tell your computer, read across the first row and put that one in here, put that one in here, that's how bright you want that pixel, then down to the next one, make that one that bright, make that one that bright, and so on and so forth. And so in that sense, a picture itself could be realized as a vector. Once you do that, then you could do some cool analysis stuff with that. The same way that my wife takes, or you could do with Beethoven's Ninth Symphony. You could analyze frequencies and stuff like that. And that's what my wife does with seismograms. She looks at the different frequencies that are happening. Like a seismic signal itself is usually a sum of a bunch of different frequencies, or a sum of sine waves. You want to think about it that way. If you take one sine wave that's at this frequency, and you take another sine wave that's at this frequency, and you add them together, you get a new thing that's maybe something like this, right? It does something like that, and blah, 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 blah. You could take Beethoven's Ninth Symphony and break that into its component frequencies. You could take a seismogram and break that into its component frequencies. You could take a picture and break it into its component frequencies. And that's how they do stuff like compression, the compression of images and stuff like that. So you have like a 10 megapixel image. You could compress it down by doing some crazy stuff like this. But my point, I just wanted to kind of end our talk about vectors, talking about vectors aren't just lines in the plane. They could be, and obviously, like, if you have a, say, 100 by 100 pixel, now you're talking about a vector that's 100 times 100 is what, 10,000? Right? So you have some vector in 10,000 space, right? Where you have 10,000 dimensions, and so what is that? Well, you don't need to necessarily think about it like that. You could, you could see how this is just a scheme for how you do this type of thing. Or you could say if you do all of Beethoven's Ninth Symphony sampled at 44,000 hertz, that would be 44,000 entries in your vector times however many seconds Beethoven's Ninth Symphony is. It's like an hour long, right? So you're talking about 60 times, like it's ridiculous. 60 times 6, so 3,600 times. It's ridiculous, right? And so, but that doesn't mean that, you're looking at a vector that's pointing in some direction, but actually it does kind of mean that too. And there's ways that if you do think about it as a vector in some higher dimensional space, like when we first started talking about this, you're like, what is this? It's a fourth dimensional vector. It could be a lot of things. It could be a picture. It could be, it could be a lot of different things. And so I just kind of wanted to talk about that, because if you go on in math, you'll be doing stuff like this, and it's really cool. But okay, guys, that's what we got today.